Hey everybody, we're going to take some notes today on piecewise linear models, and we're also going to take some notes on setting up systems of equations. And so if you all have not seen yet, I've taken pictures and I've posted pictures of these notes on Canvas. So if you would like to print those off and then just that way you don't have to draw everything and write down all of the problems, you're welcome to do that. You can focus more so on the math. So we can go ahead and get started. So we're going to be talking about piecewise linear models. So a piecewise linear model is a model made up of several straight line segments. So an example of a piecewise linear model right here is we've got the cost of printing invites or invitations depends on the number of invites printed. So you can see here on this, we got the x-axis as the number of invitations there. We've got the y-axis as the cost. And you can see after a certain point, what appears to be 150. So let's see if I can get a pin that works real quick. So at 100, 50, that there's a change in slope, a change in the piece. So we got piece 1 and we've got piece 2 here. And so we're going to use this graph to answer a couple of different questions. So the first thing is that we need to find the gradient or the slope of AB and BC, because you can see that this one is going up what looks like to be a little bit more steeply than that one. So we're going to figure out the slope of both of these, the gradient of both of these real quick. So the coordinates we're going to use, 150 is a part of both lines. For A here, we're going to use 0, 0. And then for C, we can use the coordinate, I believe that is 200, 80. And we're going to calculate some slope using those. So I'm going to stray away from the equation since we have a graph here. We go up 100 over 50. So AB, or excuse me, we go up 50 over, so that's going to be up 50 over 100. Which 50 over 100, we can reduce that to 1/2. So then, let's see here. For BC, we go up 30, it looks like, and then we go over 100. So that would be 30 over 100. Which is 3 out of 10. So if we're thinking about this in terms of cost, if we're going up 1 over 2, that's going to be an average, if we're talking in dollars, $0.50. So the way that we would interpret that is we'd say each invitation cost 50 cents up to $100 or 100 invitations, sorry. Because at that point, that is when we hit that second piece here. After 100, it moves upward. So that's how we interpret this in terms of the slope. So then for the BC here, after 100, you get a little bit of a deal here. So after 100, each cost, 3/10 of a dollar is 30 cents. So $0.30. And so that's how we can interpret what's going on there. So then we can also use this model to do a couple of other things. So the next thing that we're going to want to look at is to find the cost of printing 60 invites. So the cost for 60 invites here, we can just straight up use the graph here. It appears that it is going by 20s. So 20, 40, 60. If we put a coordinate right there, that's going to give us the coordinate 60, 30. So the cost of printing 60 invitationals, or invites, excuse me, is going to be $30. So then the last thing that we're going to figure out here is how many invites can be printed for $74. Now, unfortunately here, we cannot tell exactly where 74 is based off of this graph. We can kind of estimate it. We could probably get close, but we want to have the most concise information available here. So what we can do is we can write an equation, and then we can solve that equation here for it. So we have the slope of BC, because we're going to have to use BC because it's more than 100 invitations. So we'll say, okay, 180 invitations, or excuse me, for $74, we're going to say the coordinate here that we know, we got to write an equation here. So I'm going to use gradient slope form, m times x minus x1. The coordinate we have here is the coordinate 100, 50. So we're going to say y minus 50 equals the slope, which is 3/10, times x minus 100. And now we've got to replace what we know what the y-axis is here. So we know that the y here is 74. So we're going to write 74 minus 50 equals 3/10 times x minus 100. So I'm going to continue this equation over here. 74 minus 50 is 24. So we've got 24 equals 3/10. I'm going to go ahead and distribute that x. So 3/10 of x is just 3/10 x. 3/10 of 100 is going to be 300 divided by 10. That's going to be 30. So we're going to say minus 30 here. Now to finish solving this, we're going to add 30 to both sides, plus 30. We're going to get 54 equals 3/10x. And the way that we're going to solve that is by multiplying both sides by its reciprocal. That's how you cancel out a fraction here, is multiplying both sides. Let's see if I can find a different colored pen that works. So if we multiply both sides here by 10/3, we're going to end up getting that x is equal to 180. So we could get 180 invitations here for $74. We got to remember what we were setting out to find, what we were setting out to solve. So now the next thing that we're going to look at here, we're going to look at that is the wrong piece of notes here. Let's start here. Sorry, you all. So we're going to look at another one. So, what I've done is I've listed once we get those books, you can go back and look at those examples here. And so what we're going to be looking at now is number 1 and page 90, and that's the orange book. And what we've got here is we've got a graph that shows the relationship between household water usage and the cost of water. So it up to the first, what looks like to be 25 kiloliters here. It costs a certain rate, and then after that it shoots up. So what we're going to do again is we're going to find the slope of each segment. And we're going to interpret those. So if you want to pause it here and go ahead and do that, you are welcome to do so. I'm going to just really quickly list some coordinates so that I can do some pretty quick slope to calculate these things. That's 25, 100. And then I guess we can pick this point right here, which is 50, 200. So let's see, we go up 25. So the base rate, we'll say we go up 25, or excuse me, I need to look at the y coordinate. So we go up 50 over, let's see, we go from 0 to 25. So that's going to give me a rate of 2 there. And now we need to look at the higher rate. So looking at this graph, it looks like we go up 100 and then over 25. So the rise there is 100 over 25, which is 4. And the way that we need to interpret this, so for the first one, you see how it intercepts at 0.50 there? So if you use $0, or if you use 0 gallons or kiloliters of water, excuse me, you're going to be charged $50. So there's a base fee of $50 here for this water. And then we also, after that base rate, if it's a slope of 2, each kiloliter of water is going to cost $2, and that goes up to 25 kiloliters. So you can go ahead and interpret the other one after that. And all that that's going to be is us saying, okay, well, the higher rate, so once you get past $25, that it's going to, or 25 kiloliters, it's going to cost $4 per kiloliter. So now, the next thing it wants us to do, we want to find the cost of using 40 kiloliters of water. So again, that is one that we can easily look at here. We can say, okay, 40, where does this intersect on the graph here? 40 intersects right there at what appears to be $160. So the cost of using 40 kiloliters is just going to be $160. And then let's see, the last one here that we're going to answer using a piecewise model. Kelly's last water bill is $80. She wants to know how much water did she use. And this one, since it is perfect on the graph, if you look at this graph, we can easily find 80. This axis is going by 10, so we'll go up 3 from 50. 1, 2, 3. That intersects here. So if she used 80, she would have used, or if she got charged $80, she would have used 15 kiloliters of water. Which is a lot of water relative to a gallon, which is what we use to measure in the US. So then the last thing that we're going to look at here is one more example of a linear piecewise model. So again, I am going off of a problem from the book, so when we get those books, you will be able to look at this a little bit easier. Until then, I will just draw out what you need, post pictures of the notes for you all to take pictures of. So we've got a package shipping company, and basically the way that they determine how much it's going to cost to ship something is based off the weight. So if something costs anything that's below or up to 500 grams is going to cost $13. If it's going to be over 500 and up to 1 kilogram, it's going to be $23, and so on and so forth. So what we've got to do is we've got to draw a graph to display this information. And what we're going to get is something that looks a little bit interesting. So let's see. The weight is our x-axis here, so we'll start it at 0. So we'll go 1, 2, 3, 4, 5, and 6. And then let's see, the highest we go up is 40, but we also have to graph up to $5 extra per kilogram, so we'll go by 10. So we'll go 10. We're going to scratch that out. 10, 20, 30, 40, 50, 60. So it says that up to 500 grams, which is half a kilogram, it's going to cost $13. So from this point, from 0 all the way to halfway here, it's going to cost, and we're going to put an open dot here because at 500, or we're going to put a closed dot, excuse me, because up to 500 grams, it's going to cost $13. Now, when we bump up to the next one, when we bump up to over 500 and up to 1 kilogram, so we're going to put at 23 here, we're going to put an open dot because 500 is not included for this 23 price. So we're going to put an open dot, and we're going to have it go all the way out to 1 kilogram, and that's going to end in a closed dot because 1 kilogram is included here. Now, on the next one, we're going to go to, so from 1 kilogram to 2 kilograms here, it's going to cost 32. So we're going to go up to 32. We're going to put an open dot here. Now that's going to span all the way over to 2. So it's going to be a little bit longer. And it's up to 2 grams, or 2 kilograms rather. So now we're going to say, okay, so from over 2 grams to up to 3 kilograms, it's $40. So we're going to go up to 40. Open dot here to start, and it's going to go all the way over to 3. And then we have to say, okay, extra kilogram up to that point is going to be $5 extra. So from 3, we're going to put an open dot all the way to 4. It's going to be $45. And then we're going to graph one last thing, say, okay, the last one is going to go up to $50. If it's 5 kilograms, it's going to stretch from 4 all the way to 5. And so we have here what's called a step function. It kind of looks like steps that you could walk up. And this is one of the more common types of piecewise functions that you'll see in the real world. So what we can do is once we have this listed, we can go ahead and say, okay, well, find the cost of different packages weighing this price. So if something was 750 grams, this is in kilograms, so that's going to be 0.75. So 0.75, that would go up to this piece right here. So that would be $23. If we did 1.6 kilograms, we'd go to here. That would go to this piece right here, and that would be $32. And then lastly, the 3.4, if we go to 3.4 and go up to that piece, that's going to be $45. And then the last thing that we can answer here is if you have a 1.7 and a 2.8 kilogram parcel to send, how much will you save by sending a single package? And so when we're looking at that, one of the things is it a better deal to send them together as one package or 2 individually? So if we look at that, a 1.7 kilogram package, 1.7 would cost $32. And we'd have to add that to the 2.8, which would cost $40. So that, if we sent them together, would cost $72. And then if we combine their weight, so 1.7 and 2.8, and so that would be 4.5 pounds or kilograms. So 4.5, and we went up, that would cost us $50. So 4.5 kg would be, we'd have to pay $50 for that. So as far as piecewise functions go, they're not overly complicated. They do not require, they're not a whole lot different than regular linear models. They're just pieces to them. So if you all have any questions on those at all, you are welcome to stop by in Zoom and ask, and you all have a good rest of your day. So the second topic that we have for today is working with systems of equations as models And we're mainly going to use technology to solve those today, as opposed to using substitution or elimination or graphing. So you can take a collective sigh very quickly. Now, the thing is, if we've got data points, if we got values that a model is supposed to fit, what we can do is we can substitute those points into a function to create a system. And from there, once we have a system, we can write equations that we can solve and go from there. So what that looks like is, for example, if we've got this table that shows the quantity of air affected by smoke after a fire started. So we've got our seconds here and we've got our liters here. The important thing is right here, we've got this model that says that this is going to follow this equation right here. And we've got these data points right here that we've collected. So if we know the general model that something's supposed to follow, and we've got some data points, we can write an equation to do so. So all we're going to do is try to write an equation to do this using these data points. So what we're going to do is we're going to sub in these values here to do that. So I'm going to sub in the coordinate 1, 2 into this equation up here to get something that I can write. So what that looks like now is we're going to say, okay, well, V is 2, so 2 equals A times 1 cubed, because this is T, this is V here. So we're going to say plus B times 1 squared plus C times 1. Next coordinate we're going to use is 2, 4. That's our other data point. So we're going to say 4 equals A times 2 cubed plus B times 2 squared plus C times 2. And the last coordinate we're going to use is 3, 12. We're going to say 12 equals A times 3 cubed plus B times 3 squared plus C times 3. So now what we're going to do from there is we're going to simplify these equations. So we're going to get 2 equals A times 1 cubed is just going to be A plus B plus C. I'm going to simplify this. We're going to get 4 equals 8A plus 4B plus 2C. We've got 12 equals 27A plus 9B plus 3C. So now we've got a system of equations that we could write and we could solve to figure this out. So what I want you all to do real quick is stop this video wherever you're at. So I have 2 links in Canvas. One is if you have a TI-84 calculator at home, and one is if you do not. We could use substitution, elimination, or graphing to solve these, but we are not going to, because we know that you all can do that, and the algebra is going to take time away from that. And when you all see this on the IB test, they're not going to expect you to solve these by hand. So we're going to use polysmalt or simultaneous equation solver. They're the exact same thing. So that program that I've linked is called polysmalt 2. And what we end up getting is that the values of A is 1, the value of B is -3, and the value of C is 4. And all that we're going to do with that is we're going to substitute those values in up here to have an equation that we could now make predictions off of. So we're going to say V equals 1t cubed plus, not plus, it's going to be minus 3t squared plus 4t. And that the whole reason that we want to write a model is that we can try to use a model to make predictions within the model, which is interpolation, and we can use it to make predictions outside the model, which is extrapolation. So we're going to look at another example here. And there's not a model, this is just a line to make sure that we can, that we're grasping this. So we want to use technology to find a model for this line right here. Now, it's in the form of y equals ax plus b. So the first thing that we've got to do is we've got to write that equation. So again, these are x and y coordinates, x and y coordinates. So the two equations that we're going to write are substituting x and y into here. So if we did 12 comma 7, y is going to be 7. So we're going to say 7 equals, that's going to be 12a plus b. And then if we use 4 comma 3, that's going to be 3 equals what? 4a plus b. And so what I want you all to do real quick, use Polysmalt 2 or use that simultaneous equation solver online that I sent you all and see if you can do that. And we're going to check our answers here by using a little bit of algebra. So let's see here. We're going to solve these two equations using some algebra, because when it's a 2 by 2, it's very easy to verify. So right now, these are set up for elimination already. The b's are the same sign. So we're going to subtract here to get that these b's cancel. 12 minus 4a is going to give us 8a. 7 minus 3 is going to give us 4. So then 8 times what is going to give us 4. We're going to divide there. So we're going to get 1/2 equals a, or 0.5. And then the other, so that means that b is going to be the value of 1. So you all can verify that using Polysmalt, but that's how you would check your answer algebraically. So to wrap up today, I want to look at one last thing. So we're going to be using the same model here, except now we're looking at the distance a scooter has traveled after t seconds. So somebody was really into the study of how scooters move, and they said this equation right here is the regression equation, and we recorded some data here. So we want to use that to try and make predictions down the line. So when we write these, we're going to have to use these coordinates again. So 1, 1.7, 4, 7.2, 9, and 23.7. And substitute those in. So what I want you all to do is see if you all can do this one on your own, and I'm going to post the answer to that on Canvas for after you've watched this. So if you guys have any questions at all, I want you all to stop by Zoom, let me know, and we can go from there. Thanks, y'all.